Hello, welcome to this lesson on solving simultaneous linear equations. Again, we'll be looking at methods of elimination. By the end of this lesson, you should be able to solve a system of linear equations in two unknowns using the elimination method. Do you remember what we did in the previous lesson? We found ways to get rid of or eliminate the x or the y in an equation. We did some clever adding or subtracting of two whole equations. Sometimes we also had to multiply each term in the equation by a number. This was all to get rid of either the x or the y so that we could solve the equations. In this lesson, we will work with ways of using elimination that aren't immediately obvious, and we will need some careful planning. Solve for x and y. Look at the two equations and the unknowns carefully. What would make sense? Should we try to get rid of or eliminate the x's or the y's? To get rid of the x's, I could multiply this here by 2. Now, if we wanted to get rid of the y's, I could also multiply the y's by 2. What should I do now? We have two simplified equations with the x's and the y's all lined up. Should we add the equations or subtract them? To eliminate the x's, it would make sense to add. So, equation 2 plus equation 3 will give me minus 8x plus 8x, which gives me 0. 6y minus 6y, which gives me 0, is equal to minus 20 plus 50, which gives me 30. Oops, both the unknowns have disappeared, and we are left with 0 is equal to 30. But that makes no sense. It's not true at all. Now, does this remind you of anything we've did previously? It means that there is no solution to this equation. If there is no solution, it means that the graphs of these equations do not cut or intersect each other. Now, there's only one situation in which this happens. The lines must be parallel. Parallel lines have equal gradients. How could we check to see if the gradients of the lines are equal? Look at the equations again. If we can put them into the form y equals mx plus c, it will be easy to see what their gradients are. For equation 1, I get y is equal to 4/3 of x minus 25 divided by 3. Now, I've identified the gradient as 4 divided by 3. I also rewrote the second equation in the form of y equals mx plus c. Have a look. I ended up with y is equal to 4/3 of x minus 10 divided by 3. So what's the gradient of the graph of this line? It is also 4/3. Hey, what do you know? Both gradients are equal to 4/3. So this confirms what we thought. Since the gradients are equal, the lines must be parallel. So the lines have no intersection point, and thus there is no solution to the set of simultaneous equations. Let's look at the next example. Solve for x and y. If we use the method of substitution, we first need to get one of the unknowns on its own. In both the equations, both x and y have coefficients that are not equal to 1. This should be a warning bell for you. For us to get an unknown on its own, we will end up working with fractions. Take a look. Writing equation 1 with x on its own, I get this. So, if we were using substitution, we'd have to substitute this fraction into the other equation. It looks like a long process. Can you see that it would make more sense to use elimination? Both equations are simplified and they have the x's and y's all lined up. Great. Now we want to add or subtract them to get rid of either the x's or the y's. To get rid of the x terms, they must have the same number in the coefficient. It could be positive or negative. Now the easiest number to choose is the lowest common multiple of 4 and 3. Now what is the smallest number that both 4 and 3 can divide into? Did you get 12? This means that if I multiply equation 1 by 3, I'll get a coefficient of 12 for x. In our second equation, I need to multiply both sides of the equation by 4 in order to get a coefficient of 12 for x. It's okay to have made two new equations because they will help us eliminate the x's in the next step. Now we have 12 as our coefficient of x in both these rows. Should we add the two equations? That would give us 24x and we haven't eliminated x. So now what? If we subtract one equation from the other, the x's will drop out. Remember, be careful with the signs when you're subtracting equations. Now, we want to subtract equation 4 from equation 3. To do this, we got to remember the signs that change. 12x minus 12x gives me 0. Minus 9y plus 32y gives me positive 23y is equal to 75 plus 40, which gives me 115. We get y is equal to 115 divided by 23. This gives us y is equal to 5. Now we must solve for x. I'm going to substitute y equals 5 into equation 1. We get 4x minus 3 times 5 is equal to 25. This simplifies to 4x is equal to 25 plus 15, which gives me 4x equal to 40. Dividing by 4 on both sides gives us x equals to 10. So our simultaneous solution is x equal to 10 and y equal to 5. Now, which method do you think was easier for this set of simultaneous equations? I think the elimination was easier. Remember what we learned in this example. If none of the coefficients are 1 or minus 1 in any of our equations, then the elimination method may be a better option than substitution. Do you feel confident to do another example? Look at these equations. Solve the following simultaneous equations for x and y. Where do we begin? It makes sense to simplify this equation with the fractions. So multiply every term in the equation by the lowest common denominator, or LCD, which is 3 times 2, or 6 in this case. Here I can divide the 3 into 3 once, and the 3 goes into 6 twice. Here, there's nothing I can do to simplify further. On the right hand side, the 2 goes into 2 once and the 2 goes into 6 3 times. We can write this as 2 multiplied by x plus 2 minus 6 is equal to 3 multiplied by 4 minus y. This simplifies to 2x plus 4 minus 6 is equal to 12 minus 3y. We get 2x plus 3y is equal to 12 plus 6 minus 4, which gives me 14. We'll call this equation 3. Let's see if this has helped us. We have equations 1 and 3 here. Can we eliminate one of the unknowns now? It keeps the calculation smaller if you choose the unknown with the smaller coefficients. In this question, I'll choose to get rid of y. The lowest common multiple between this coefficient 2 and this coefficient 3 is 6. This means that I must first multiply equation 1 by 3. For the second equation, I need to multiply by 2. Now you can decide. Will you add the two new equations or subtract them? Remember that we want to get rid of one unknown, so it makes sense to subtract and get rid of the y's. We need to subtract equation 5 from equation 4. Remember, we're subtracting, so we need to change the signs. 15x minus 4x is equal to 11x. 6y minus 6y gives me 0y, which is equal to 72 minus 28, which gives me 44. To get x, I need to divide by 11 on both sides. I get x is equal to 4. We're nearly at the end. We just now need to find y. We can do this by substituting x equals to 4 into any equation. If we substitute x as 4 in equation 1, we get 5 multiplied by 4 plus 2y is equal to 24. This gives us 20 plus 2y is equal to 24. We get 2y is equal to 24 minus 20, which is 4, and this simplifies to y is equal to 2. That's it. Our solution is complete. It is the ordered pair x equals to 4 and y equals to 2. Now I'll leave it to you to check that this solution satisfies both the original equations. Let's recap the steps in the elimination method. Simplify if necessary. Multiply one equation or both equations in order to eliminate one of the variables. Add or subtract equations. Solve for the remaining unknown in the new equation. Solve for the second unknown. Check the ordered pair solution in both original equations. Try this task to confirm whether you understand what we did today. Solve for x and y if 2x plus 3y is equal to 25 and 3x minus 5y is equal to 28. In our next lesson, we'll look at some interesting applications of simultaneous equations. Goodbye. Bye.